All right. So today we'll be talking about Arduino. So, or I guess it's a bit more broadly just microcontrollers and electronics. So an Arduino is an example of a microcontroller, and a microcontroller is just a chip. It's like a miniature computer, and it's capable of doing some smarter things with our circuits. It lets us write code that influences the way that our circuits behave. So if we want to do fancy things with our electronics, we don't need to do it all just analog and using switches that you manually flip and stuff. But this lets you do lots of that in software, which is quite nice. So it opens up a whole new possibility of things to do. So normally I'd be showing you all Arduinos and you get to play with them and build them by hand, like the little kits with them. But obviously, seeing as this is all done remotely, we'll have to settle for something like Tinkercad. But on Tinkercad, here's an example of an Arduino board. There are many Arduino boards, and not every microcontroller is an Arduino, so I'll show a couple other examples of things like that in a second. But this here is an Arduino Uno board. So this is one of the most popular starter ones, I would reckon, though there are bigger ones, smaller ones for different purposes. But the basic layout of the board is this chunk here is where the actual microcontroller itself is. So, and this is actually on a real board something that you can like pull in and then slot in a new one. So if for some reason your chip breaks, the for some reason being if you manage to hook something up wrong and fry it or something, you can get a new one, just slot it in. So that's the brain of the board, if you will. Then it has some other useful things on it. That there is a reset button, so in the real world, or actually maybe even in the simulation, probably not in the simulation. Can we press the button in the simulation? No, there's no code there anyways. But that's like a reset button, so if you want to rerun your program or like reboot the computer, you'd press that button. Here's a big USB connection, that's how you program it, connect it to a computer. That's a place for like power. It's a little bit like some of the older laptop power connectors with the circular barrel jacks. It's got a couple of LEDs on it that you can play with. There's another one. And then some miscellaneous chips around. I think that one's for USB communication. That's a clock. So it just ticks kind of repetitively, and that's how the Arduino can do timing. It's a very well or precisely timed ticking. And then some other things, these are capacitors for like power stuff. But you probably won't need to deal with much of that aside from like knowing where to plug it into the computer and how to restart it. What you will be dealing with, probably much more, are all of these things here. So every one of these, and it's a bit hard to tell because we're looking at these one-dimensionally. I'll show you in a second what they look like on an actual board. But there are little holes that you can connect wires into. And each one of these different wires is connected to some different part of the board, and many of them, as in most of these and these ones, are controlled by this little computer here. So you can program or write programs that make them do different things, which is quite exciting. So I'll show you what a couple of these look like in real life. So here's Arduino's website. They make a bunch of different Arduinos, and by a bunch I mean like a ridiculous number. But up here, the first one they show is the Arduino Uno. That's the one that we have in our simulation of Tinkercad. So it looks a bit like that in the real world. So see, those bits are like little plastic ports that kind of come upwards, and you can plug little cables into them. And then there's the power thing, the chip itself. There's the USB connection. It's one of those big fat USB connections. Technically, I think they're called printer connections, but I doubt many of you have had to connect USB printers with that port before. But in case you have. So that's what an Arduino Uno looks like in the real world, or a picture of what it would look like in the real world. It's also worth saying they are far from the only microcontrollers in the world. Another very, very popular one that if any of you are doing engineering, you might end up playing with a couple of times if you're in like the AXI side of things for like systems control. That's an ESP32. These things are compatible with lots of the Arduino stuff, but they're smaller, cheaper, and they can connect to Wi-Fi and Bluetooth. I personally love them. I'll try and avoid showing too many things on webcam today since it's not like being properly recorded for other people, but I might have, yeah. For the people who can see the webcam, here is an ESP32 in the real world. Very, very tiny, very cute little things. And they've got a tiny USB connection there, 2 little buttons, and then all their ports stick out as pins on the bottom of it instead of on the top. So this one here is stuck in a breadboard, but you can see it's got those little pokey bits that goes into a breadboard on the bottom. So those are pretty cool if you ever run across them. And there's a bunch of them in the world, these microcontrollers in general. Some of them will be much more specialist if you're building your own circuit boards, but Arduino is sometimes a little blanket term for beginners working with electronics like this. So yes, that is what we'll be focusing on today, are the Arduinos. So, I'll let them in. Excellent. So I think today's plan is going to be pretty simple. We're going to go through and build a couple of basic circuits with this Arduino, gradually building up in complexity, and eventually the idea will be to build something a bit like this. So, haha, I will hide the secret code. But our final goal, if you will, after these 2 sessions will be to build a project something like this, where you can put in on a pin pad some angle, and this motor will move to that angle. So we could put in 0 degrees, and then go, and it goes to 0 degrees, 90 degrees, and then go, which will go to halfway, and it can also go up to 180. So this is an example of a servo motor. You may not have seen them before, you may have. But their main draw is that they go to a particular position very exactly, and they can hold that position for you. So they're very precise and can do very delicate movements. However, unlike a normal motor or a DC motor, they can't go full circles. So most servos can only do 180 degrees, so they can kind of wiper back and forth. There are some that do 720 degrees, and then there are some that do rotate continuously. So there's a bunch of different types, but this is just a 180 degree one. But we'll get into how to do all of that in a little bit as we grow our knowledge. But I think our first thing to do would be the basic example. So just like how when we did Python, or if you've ever done any other programming language tutorial, you've probably seen a hello world program. So you just write a program that prints hello world to the screen, and that's like the starter program. The equivalent for microcontrollers and things like Arduino is to make an LED blink. So we can write a bit of a blinking program. So I think that's where we should start. So I'll ask a couple of questions, just so I can get a feel. How many people were at the electronics session last week? And I'll do a poll. Session last week. Or no Ohm's law, because that's really all we need. Wonderful. And you don't need to be an expert with it, but... Okay, so a bit of a mix. I think that should be alright. I'll go over what we're doing in a bit of a review. So since there are some of you who have, I'll ask you the question that I'm going to try and work out first, and then I'll work it out as well. And then we can go from there. But we will start with a breadboard. So we'll bread out a breadboard here so we can connect some things up. Now, this Arduino board here has... Can I rotate that? Sure can. Alright. Now all the things are upside down. That's a bit annoying, actually. I'm gonna not have that that way. So there we are. Should be easy to read. Okie dokie. For the people who did make the electronic session or are familiar with breadboards, this Arduino here has a couple of different power outputs. So this one here, this V-in, that's a power input. So you can power it via that, although ours is going to be powered via this USB connection. And then there's this ground here, which is like the negative voltage, or it's just a 0 reference voltage, but that's the minus sign. And then we have 2 different options for a positive voltage, a 5 volt and a 3.3 volt. We'll probably want to use the 5 volt for what we're playing with, but we could use either. But if I wanted to connect these power connectors here to this breadboard, what would be the most, I guess, reasonable way to do so? Where should, say, I take this cable, which is coming from ground. Where should this get connected on this breadboard? In like a best practice kind of way. Any ideas? And you can answer wherever you please in either the Discord or there. A rail, I agree. Which one of the rails? I mean, not that it particularly matters, but one of them is labeled more sensibly for the matter. Yes, top or the bottom one with a minus. I would agree. What are we feeling? Top or bottom? I'm going to do the... Well, both of them are not ideally lined out. I'll do the bottom one. Why not? So there we are. So that's hooked up there, which means, of course, because it's a breadboard, that this entire row here, all of this is essentially connected to that ground port. Excellent. So, yeah, it doesn't really matter. Yeah, it can be plus as well. That is true. It's just neater when it's a minus sign here. It's generally good when you're working with electronics to think about the poor, clueless you of the future so that you don't accidentally shoot yourself in the foot. If you do mix up the rails, then in the future, like, you're wanting a positive voltage and you connect to the plus, but really that's the negative voltage, then you could like unnecessarily break things. But it's easy to forget these things. I've broken plenty of things like this, so yes, it can be either, but it is definitely good to follow a sensible practice. Wonderful. And then very similarly, we would take this positive rail and we would connect that up to 5 volts in this example. Oh no, burnt a 3D printer board that way. Oh, that's tragic. Yeah, so there are many casualties in electronics. Most of them don't need to happen, but they do, because we all get a bit silly. Wonderful. Okay. So those are connected to the power rail. That's fantastic. We have a power breadboard now. If we want, we can double check that. Well, actually we can't just quite yet, but we'll be able to very soon. Yeah, we'll build our full circuit first. Okay, additionally, we have an LED. Where should this LED go on the board? Does anyone have any opinions? And you don't have to be terribly exact. In 2 different rows. Yes, I think that is a good idea, Jacob. So, what he means by 2 different rows is that these 2 legs of the LED that are coming out the bottom of it should be connected into electrically separate parts of the breadboard. So if we connect it this way, then this pin is unconnected to this pin, so they're not the same, which is good. That's what we want. But if we were to connect it, say, in a different way, like this, then we would have an issue, because now the negative and the positive are connected directly together, so you're kind of shorting out that component. So it wouldn't turn on. Wonderful. All right, so I agree. 2 different rows is a good idea. I'll put it way up at the top so we have plenty of room. Okay. Now, does anybody remember, or well, what should we do next? Should we just connect it up to power? Does that sound like something we could do? Or are there any other components that we might want on our board? Long leg goes to plus, short to ground, plus a resistor. Yes, a resistor is needed. Wonderful, yes. So a couple of you spotted that we need a resistor, and you've additionally spotted which one of the legs should go to plus and which one to ground. So this is where our little Ohm's Law thingy comes in that we get to play with. This LED, I know because I've experimented with it before, and in fact we can see it because it's just a simulation. There's no harm in virtually breaking it. But if you run too much power through an LED, and this power is in the form of, because the voltage is constant across an LED, so the power is just the current, related directly to the current, they're mostly limited at 20 milliamps, and anything more than that kind of roasts them. So we'll be able to see that in a second. So first what we'll do is not follow the good advice we've been given, since this is just a virtual environment and we can break things recklessly. And we'll connect up this longer leg to positive, and then the shorter leg to ground. And then we'll start the simulation, except I don't think this will run because the code isn't anywhere near valid. Right. Okay. I will paste something in here, or just type something out real quick, and we'll explain it once we get to it. We don't need to worry about it too much just yet. So it's just totally empty code for the time being. but hopefully they should get it to at least not complain too loudly at us. Boop, boop, boop. Yes, wonderful, cool, and we see what we were looking out for. So, our LED has this little explosion symbol on it. Now, in real life, your LED probably won't explode, but it will break. And it's telling us here that the current through the LED is a whopping 483 milliamps, but the absolute maximum is 20. So, what we need to do, as was pointed out by Philip and Jacob, was add a resistor to our circuit. And this resistor, if you remember from our Ohm's law, which was, I don't have a great place to type this. Well, we'll just Google it because you can see it. But it's V equals IR. Well, good job, Brooks. That was really a complete sentence. Yes, so there we are. V equals IR. So that's the equation that will help us calculate what resistance we need at 5 volts to limit the current to 20 milliamps. Now, it's complicated slightly by the fact that the LED itself takes up a voltage. So if we want, we can actually measure that real quickly, and then we can determine what value of a resistor we should use. So we'll stop our simulation real quick. We'll get our multimeter, which we saw last time around. It's in voltage mode, which is fantastic. And then we can just take it and connect it in parallel, because voltage goes in parallel, across the LED. And theoretically, this should work. Yes, wonderful. Oh, okay, so just 5 volt because it's broken. Alright, fair enough. So, what we'll do is first we'll just calculate it, assuming that well, here's what I'll do. I'll Google how much the forward drop voltage on a typical LED is. So, typical LED drop voltage. I think it should be between. Yes, so I agree, Jacob. I think that is about a good value for a resistor. Okay, so it looks like a typical forward voltage is between those. It varies from the color of the LED. Red LED typically 1.7 to 2. Okay, excellent. So we have a red LED. So how LEDs work is they kind of just consume a fixed amount of voltage. And in our case, we'll assume on the safe side that it consumes the smaller amount. So we'll say this consumes 1.7 of the 5 volts, which means the rest of the voltage needs to be dropped across the resistor that we add. So if we have and I'll type this in the Google Meet chat. Yeah, so if we have 5 volts total, and 1.7 volts dropped on the LED, what resistor value do we need to limit the current at 20 milliamps? All right, so that is people's little challenge. I'll give people a minute or two to solve that probably. Are there any questions right off the bat about how we might go about that? Because I think essentially all you'll need is Ohm's law, and I guess if you want to be particularly exhaustive, the Kirchhoff's voltage law applies here as well, which is the one that says around a loop, the sum of voltages is 0. So we'll be losing some amount across a resistor, losing some amount across the LED, and then adding 5 volts. So basically, the voltage lost here and the voltage lost here just need to add to 5. So we want to calculate what value of resistor would give us that current. Well, we know how much voltage, yeah, so we'll be dropped. Okay, we'll ask it in parts. So the first question is, how much voltage does the resistor need to drop according to Kirchhoff's voltage law? So we have a 5 volt source, 1.7 is lost on the LED. What remaining voltage is lost? Yes, fantastic. I would agree, 3.3. Wonderful. Now that we have our 3.3 voltage, that's the voltage we want in Ohm's law. So we know that we want, well, that it's going to have 3.3 volts across it. And we also know that we want 20 milliamps to go through it. So we have the voltage, we have the current, all we need to calculate is the resistance. So I'll let people give me some resistance values from that calculation. And I'll give you all a second to do that. I'll pull up my sneaky calculator and do it off screen. Whoa, how sneaky. Hey, look at that. That looks like a pretty reasonable answer. I'll double check with my own, seeing as I haven't actually done that yet, but I think that's exactly what I'll end up with. Yes, I need to remember. Lovely. Yes. Yeah, okay, I got that as well. Yes, so I concur that it is 165 ohms, and that would be enough to limit us up at 20 millivolts, 20 milliamps. So I would agree with that calculation. Excellent. And like I think it was Jacob that pointed out earlier, yeah, you can also, most tutorials and things will recommend like 200 to 330 ohms, and to be fair, that's quite valid. Part of the reason that they would be recommending values up there is because resistors don't actually come in every single value possible. They come in particular set values, and 330 ohms are a very popular size, and I think maybe it's 220 that's decently popular as well. But in our case, since it's just a simulation, we can put on our exact amount and see how close our calculation comes. So I agree that it should be 165 ohms. So we'll connect up our resistor, and it can go either on the positive side or the negative side as long as it's in series. So we'll have to move one of these wires here to connect our resistor. So I'll get rid of our negative one. I'll grab our resistor here. I'll rotate it sideways, and then we'll put it in like this. So now we'll have our power come in, goes through the LED, comes out, gonna hit our resistor, goes through our resistor, and then we'll take it, I'll move that up one, and then we'll take it from there down to negative voltage. Wonderful. Yep, that looks all right. Then we can put in our value of resistance, theoretically. Maybe. Yeah, there we are. We want to go to ohms, and 165. Stellar. Okay. Lovely. So now we can give it a test. So we'll go ahead and start our simulation like we did last time. And hey, look at that. Our LED is no longer breaking. So we no longer have the little explodey sign telling us that we've broken something. If we want to measure the current, we can do that as well with our multimeter. Does anybody remember how we need to connect a multimeter if we're measuring current, not voltage? And yes, fantastic, series, well done, Maria. I would agree with that entirely. So we'll go ahead and grab our multimeter. I'll put it up here. We'll switch it to amperage, that's the unit of current. And I'll put the positive leg into the positive power, and the negative one goes out in series to the LED. So power comes out of positive end, goes through our multimeter, into the LED, through the resistor, and then back down to 0. All right, if we run that, we get 17.8 milliamps, which is pretty close to our target of 20 milliamps. And if you're wondering why it's off, it's important to remember that that voltage I guessed, the 1.7, was exactly that, a guess. Different LEDs or different colors have different voltage drops, and red is between 1.7 and 2. So it would be in that range. A little off is okay, as long as it's off in the under direction and not in the over direction, because then you could be shortening the life of the LED. But I think we've done a quite good job of that. Wonderful. So I'll go ahead and reconnect that up the same way we had it originally. And go ahead and run that. Okay, so now the challenge becomes, we've used this little Arduino, but we've not actually done anything smart with it yet. We've just used it as a glorified power supply. But we have a circuit for lighting up an LED. Now what we want to do is blink the LED. So here is where the coding bit actually comes into things. So we can pop open our sneaky code panel over here. And then just to double check before we get too far into things. Oh, whoops, I have to stop the simulation to write code, of course. Can everyone see this? All right. And I could do a poll. I'll just see if one person can see it. I assume most of you can see it decently. Can you all read the text here, or should I make it bigger for you? Zoom it in slightly. Yes, I can certainly do so. Not with that button. Yes, I see. Wonderful. We'll go up to something massive. How's that? And we can move that over there. Is this better? Is that easier to read there, Jacob? Fantastic. Okay, wonderful. Lovely. Stellar. So we've just met our first thing. Well, okay, a bit of context first. Before we've done programming in Python, if you made it to those early bootcamp sessions, or maybe you've seen some other languages before, but the Arduino programming language, it's a bit of its own thing, but it's mostly something called C++. And C++ and Python are quite different languages. However, I personally think that the most difficult part of programming is knowing how to turn your ideas into something that is understandable by a computer, in that it's like a very specific sequence of instructions and things. So I think that learning a second programming language is much easier than learning your first one. So I won't dive too deeply into the actual features and stuff of C++ as we did with Python, but instead we'll try and translate what we can over, and I'll definitely be sure to obviously explain all of the new crazy stuff that's going to be going on. So the first new crazy thing is this line here. Does anybody want to guess what this line is and what it would translate to in Python, if you remember your Python as well? Any ideas what the first line is? Just the one that's highlighted. Exactly. Well, yes, yeah. So, right. Oh, well, I guess the one that was highlighted. So I guess I didn't really specify if it was this one or this one here. So, sorry about that. So, Philip is correct. This is a function definition, yeah. This here is just a comment, so the computer totally ignores it. That's the equivalent of, in Python, we started our comments with the hash sign, but in C++ or the Arduino language, you do 2 forward slashes like that, and then everything after you write, totally ignored by the computer, and it doesn't care at all about it. So that's good to know, just so you know that the computer's not interpreting those. And then, as was pointed out, the other highlighted line, sorry for my own ambiguity there, is a setup function. So Arduino is different from C++ in that it gives you these two special functions. And how they work is everything inside of these curly brackets gets run exactly once when the Arduino is first turned on, or I guess every time you press this reset button. And then this loop code just runs continuously over and over and over again, infinitely. So that's how you can make it do some different things. So if you want something to happen once, like when you're setting something up, hence the name of the function, you would put it into the setup. But if you want something to happen on a loop, you put it in a loop. So those are just some constructs that they give you right off the bat. To explain this funky void thing, if you recall from Python, you had functions that could return things. So say you had, you'd probably be a function, so we'll say add to, so here, this is Python that I'm showing here, just so you can map things between the two languages. This isn't actually valid code in C++. But you'd have something like this maybe, and then you would return x plus y. So that's how you would return something from a Python function, and the output here would be x plus y. What C++ does is flips that around a little bit, and you have to tell the language the types of the things that you'll be outputting in advance. What void means is that I'm outputting nothing. If you wanted to output a number, for example, you would change this to be int setup, and then you would do, quite similar to Python, you would return some integer, which is just a whole number, like that. But these basic functions are voids. They don't return anything, so they're just a chunk of code that gets run, but they don't return a value. So that is what void means, is it's just something that does not return a value. And for the most part, you won't need to worry too much about that. We might get into functions maybe on our second session, how you write them in a bit more detail, but it's nothing to be too worried about now. Excellent. So first thing we need to do when we're working with this little Arduino language is, inside of our setup, we need to well, actually, okay. Backing up, the first thing we need to do is change the way the circuit is connected to the Arduino itself, because currently it's just connected to the whole board's 5-volt power, so it will never really turn off. Unless, of course, the whole board goes off, but that's not what we want. We want to be able to control it. So to do that, what we need to do is use some different connectors. So first thing we'll do is we'll come over here and we'll delete these wires. Well, I'll try and delete these wires. I need to make the code go away. So I'll delete this wire here and this one here. And just for the sake of keeping things like cleanish, I'll move that to the other side of the board, because the connections that we care about are all of these digital pins. So you can tell they're digital pins because it's labeled here on the Arduino. It says digital. And if it's a bit difficult to read this bit, well, actually I can zoom in, don't I? I don't need to tell you. There you are. So it says digital here. All of these pins are digital pins, which means they can either be 1 or 0, so only one of two values. And 1 means there's a positive voltage there, so that would be equivalent of like our 5-volt. And 0 means they're at the ground state, or there's no voltage there, so that would be the low state. So we'll see how that works in just a second. But what we can do is just connect up any of these pins that we want to this power rail instead. So, well, we'll keep one of them just ground. So we'll keep ground to the negative rail. And then we'll take a random connector here, let's say 6, and we'll connect that to the power one. So now what we can do is when we turn on and off pin 6, and we'll see how to do that in software, we're basically turning on and off the power to, wow, well that was far from what I intended to do. We can turn on and off the power on this board here, which will effectively turn on and off our LED. So, to show that in action, we'll pop our code back open again, now that we have it connected up in a sensible way. Something that's sometimes nice to do, and this is an optional part, you can define a variable that stores your pin assignments. So it tells you what pin is responsible for what. It basically just gives a number a nicer name for you to work with. So I'll do that just to show off how it works. The recommended way to do this in the Arduino language is probably to do something... so variables here are a bit different from Python. In Python, we got very lucky because Python figures out the type of our data for us automatically. So we just need to give it a name and an equal sign. But in C++, this language, you have to tell it what type of data you're going to be storing. So in this case, our type of data is going to be an integer because it's just a number, a whole number because you can't have like a half pin. We just have whole number pins, 1, 2, 3, 4, and onwards. So we can create an integer with the keyword int, and then you give it its name. So we'll say LED pin, and we'll set that to be pin 6. Now another new thing about C++ is, unlike Python, which treats every line as, I guess, a separate chunk of code to be read, and then requires indentation to decide what's in a block, C++ uses these brackets here to say what's in a block. So anything actually inside of these brackets is in the block. It doesn't matter how it's indented. And you need to use semicolons to tell it when you're done with a line, because you can actually put several lines in one, and you just separate them with semicolons. So a bit different, but it's basically just superficial, these particular differences. The one last thing we'll probably want to do, shouldn't that be equal mark? Can you use a minus in there? Does this here look like a minus to you? Because it is definitely an equal sign. I agree that might be somewhat difficult to see, maybe, with the font that they've chosen, but I promise it's an equal sign. Looks minus-y to me too. Yes, okay, well, that's less than stellar. But yes, you're entirely correct. It should, in fact, be an equal sign. Hopefully that gets captured decently on the recording. I'll paste in the exact line in Discord, probably, because there I can format it like code. I can say CPP, and then paste it in, and then do. So yes, that is what that first line is. It is definitely an equal sign. Very, very good shout. Sorry that it looks a bit minus-y. I'll be careful, and I'll make sure everyone knows the difference when we go forward, and I'll say which one I'm using in case it's hard to see. Wonderful. Yes, and then the last thing that would be good to add on to this, and this is just a good practice thing. Your code will work both ways. but we probably won't be changing this LED pin in the code because it's a physical property of the circuit. So what you can do is add const in front of it. That means that it's a constant. So this value won't change as long as the program is running. And that lets the computer do some clever things, speeds up your program a tiny, tiny bit, and also prevents you from accidentally changing this pin later on and causing bugs. So this is probably the best practice way of doing things. You might see some other approaches to defining constant numbers or pin numbers, but this is a good default. Wonderful. So now we have a nice name, LED pin, for our pin number 6. So what we need to do is set up that pin. So what we can do in our thing here, and here I'll just to double check. Stellar. Right. So up here in our setup, first thing we need to do is change the mode that this, or tell the Arduino what mode this pin 6 is in. And what that means is that this digital pin can either be an output, so it can output a high or a low voltage, or it can sit there and it can read a high or a low voltage, and that's its input state. So in that way, it can act kind of like a binary multimeter, in that it can tell you if a voltage is high or if a voltage is low. These analog pins over here act more directly like a multimeter, and we'll get to see how those work a bit later. But in our case, this pin is going to be an output, so it's pretty, we call a function here, and it's pretty intuitively named. We do pin mode, and then in some brackets, it's just like Python, whatever you put in the brackets is an argument to that function, so it's data that gets passed into it. The first thing we need to give it is the pin number, but in our case we can use our variable that we just created. So we want to set the pin mode of the LED pin, and then we have a second argument separated with a comma, and we want this to be an output pin. And we put it in all caps because it's a constant value that Arduino has defined for us. So when you put something in all caps like that, it lets other programmers know when they read it that it's a special variable. In this case, we also have to put it this way because Arduino has made that decision for us. If we made this lowercase, it wouldn't work. So all caps for things like this constant here, output. Stellar. So that is our setup done, essentially. We just need to tell it which mode to be in, and once it's in that mode, it'll stay in that mode. Then inside of our code, what we actually want to do is turn on and off the LED. So we'll start just by turning on the LED, so we can double check that things work. So before we do that, we'll run this code, actually. We'll go ahead and run this, and we'll see that nothing happens, which is very exciting. But that's good, because we haven't actually done anything yet. So just curious, is that what that is? No, it's not. So, right, within our loop then, we need to actually tell it to do something. In this case, we're going to tell it to blink the LED. So, in doing so, what we can do is use a function called digital write. So, digital write. And then, what this is telling the Arduino is that whatever pin we give it, and again, the pin is the first argument we give it, so we'll give it our LED pin, and it will write that pin to be either a 1 or a 0, or a high or a low. So a positive or a ground voltage. So if we want to turn on our LED, we want to write a high voltage to it. This is another special word like output. So you would type in high, just like that. And be sure to end all of your lines here with semicolons. Wonderful. So if we run this, our LED should, in theory, turn on. So we'll go ahead and run it. It'll take a second. And voila! There we are. Our LED is lit up. So that is good. First place to start. But now what we want to do is make it blink. So what we could try and do, just a bit as like a first attempt, is take this and copy the line 1 down, and then just set it to low. So we've turned the LED on, then we've turned it off. So we can mark those, the comments. So turn the LED on and turn it off. And we can see how that runs. But we'll run into a bit of an issue here, and that is it looks the same. It looks like it's always on, maybe a bit dimmer perhaps. But the reason it looks exactly the same is because this loop, like I said, runs over and over and over again, really, really quickly as it possibly can. So thousands of times a second probably. And that's a bit of an issue because if you're turning it off, then you're turning it back on thousands of times a second, it just kind of looks like it's turned on constantly. So what we need to do is add a bit of a delay in there. Luckily, the Arduino people have made this very intuitive for us as well. All you need to do to add a delay is type delay, and then you tell it how long to wait for. And this is in milliseconds, so if we want it to blink every single second, we need 1,000 milliseconds. We can do that. And then over here, do another one, delay for 1,000 milliseconds afterwards. So here what we're doing is we're turning the LED on, we're waiting for 1 second, then we're turning the LED off, then we're waiting for 1 second, and because it's a loop, we're coming back up here, then we're turning it on, 1 second, off, 1 second, on, 1 second, off, 1 second, over and over and over again. So theoretically, this should blink for us. So we'll go ahead and start our simulation, and we'll wait, and et voila! There we are, a blinking LED. Blinking a bit in slow motion there, perhaps, but we can indeed see it is blinking just about once a second. So, are there any questions about this basic program here? We've seen a lot of new things. It's an entirely different programming language. But how are people feeling in general? So if there are any questions, type them out and I'll create a general poll. I'll change the way I'm phrasing that. How this works. All right. Lovely. So I put up the poll, and if anyone has any specific questions, just let me know. Seems like people are doing passably all right with it. Excellent, cool. Nice, okay. Well, if people do have questions, definitely continue to write them. But if not, I think we may move on. Aha! Why is stuff orange? You mean this here orange? I assume this setup line is what you're talking about? One of my code is too. That's an excellent question. I've never actually I've not determined why this is orange. This is a pretty specific, like, Tinkercad issue or strange thing. So the answer to your question is I'm not entirely sure. Maybe if I copy the whole thing and get rid of it and then paste it again, it'll stop misbehaving. But yeah, not entirely sure for you, unfortunately. And to answer Jacob's question, well, there you are. Luke, I think originally that line meant that there was an error, but it got stuck. That's a bug in Tinkercad, not your fault. I cut and paste my code and it's gone. So there you go. There's your answer. Nothing significant. To answer Jacob's question, can you use motors in this environment? Or motor drivers, rather. The answer is yes, I think. So you can definitely use motors. I'm not sure if they have a motor driver chip, but I think they should. So if I search motor, they have a set of different motors, yes, as well as an H-bridge motor driver. So yes, you should be able to. So Tinkercad lets you play with motors and a number of motor controllers, it looks like. So we should be set. And we'll eventually be making our way to playing with servo motors, which is what this thing here is. But those work a bit differently, obviously, than DC motors, and they don't need a motor driver because it's built into them. But yes, wonderful. Cool. Any other questions before we head on? We'll probably do analog reading next and some serial stuff. All right, if there aren't any questions, we can power onwards. All right, so our next example then. Should I keep this one or should I wreck this circuit? I'll just wreck this circuit, that's fine. The circuits are pretty simple anyways. Stellar. Okay, so what we'll do then, since we're starting fresh and working on a different project, we'll just go ahead and chop all of our code. Feel free to save yours, obviously. There's actually a download button here if you want to, like, save it. In fact, maybe that's not a bad idea, just in case. I want to upload these to the website or something later. Go ahead and save that. Lovely, and then we can go ahead and clear it back out. So, we'll go ahead and get rid of that. And remember, the only bits that we need to keep behind are just an empty loop and setup function. And then we'll also go ahead and, hey, I don't need that being that way anymore. You should stop that. Of course. Tinkercad gets a bit squirrely when you have the code editor and you're trying to use your keyboard to edit this at the same time. So just a heads up, if you're ever pressing buttons and they're not doing what you think they should, make sure the code panel is closed, I guess. All right. So, for this next set, what we're going to be doing is showing off a couple of features of the Arduino. The first will be this set of analog inputs that I mentioned a second ago. So those are a bit, they act a bit like a multimeter and can measure the voltage across things, and it's not just a 1 or a 0, but it can actually be a different number in between. So that's what we'll be using there. And in addition to that, we'll be measuring this voltage across a potentiometer, which may be a component you've not seen before. So a potentiometer is also called a variable resistor. But how this works is you run power through it in one direction. So say put 5 volts here, 0 volts here, and inside there's this like very resistive circular wire that goes around the outside. And there's this metal wiper that touches that wire and is connected to this middle pin. So essentially, as you turn this dial around this way, the electricity has to go farther through this resistive thing to get to the wiper and then to get out and into your circuit. So you can change how much resistance this has by turning a knob. I'll show you what one of these looks like in real life as well, because that's a bit of an interesting view. Potentiometer. That's what they look like in real life. So you have a bit that you turn on top, and then typically 3 outputs on the bottom. Oh yes, fantastic. And here's the diagram of how they work internally. So you have the big resistance around the outside. You put some power here, so it starts at like say 5 volts, goes down to 0 volts by this side, and depending on where you position this wiper, you can get any value between that 0 and 5 volts, is the idea. Wonderful. Cool, so what we will do is use one of those, and we're going to have the Arduino read the voltage that it's getting from this potentiometer, and then output it to something called the serial console, which we'll see what that is in just a moment. So the first thing we'll do is connect to this potentiometer in a sane way. So I'll just stick it into the breadboard there. It doesn't matter which way you run the power, it'll just change which way it is up and down on the knob, essentially. So we'll put on our power and our ground into the power rails, and I'll take 5 volts to the left side and 0 volts to the right side. So as we go around with our dial, so as we turn it this way, the voltage will go down, and we can measure that. How can we measure that? Well, we can measure that using these analog pins. So I'll connect analog 0 up to this middle column here, which is connected to that wiper pin. So that's the bit that will be influenced when we turn the knob. Wonderful. So that is, in this case, our very simple and complete circuit. So now it's just on to the code bit, which is the bit that's new. So we'll jump into our code panel and then get into our setup. So in our setup, we no longer need to do setting of modes because these analog pins are always inputs. There are no analog outputs, no real analog outputs on an Arduino. These PWM pins, which are these ones that have this squiggly sign next to them, so like 3 and 5 and 6 and 9 and 10, those can kind of fake an analog output, but what they really do is they're either a 0 or a 1, but they just kind of like go between the two very quickly, and then by varying the amount of time, they can vary the perceived voltage a little bit. So you can kind of fake an analog output. We'll get into that actually perhaps at the end of the day, hopefully when we have time. But first, we're going to talk about how the analog inputs work. So since you don't need to set up the analog inputs, we'll actually put nothing for that here. However, if we want to write out to this serial monitor, so it's just like a bit of an output place for text. You can send text to the Arduino. So you can say like hello and then press the send button and send it in. Or you can read what the Arduino prints to this way. In the real world, this signal is sent over this USB cable, and the serial monitor is on your computer. So the serial monitor you can read on your computer from like the Arduino IDE, and you can see what this is outputting. It also has a graphing feature, which is kind of cool, but not something we'll probably play with extensively. Well, actually, we'll be able to play with it in this example, I think. Stellar. All right, so what we need to do is set up the serial console. So to do that, we say serial, a big capital letter, and then you do a dot. And this is actually very similar to how it works in Python. A dot and then something afterwards is a method. So it's a function that's being called on this object, and this object is the serial object, and that's given to us already. So what do we want to do with the serial object? We want to begin the serial transmission. So we use begin. And the last thing we need to do is within these little brackets here, we need to tell it at what speed we want to communicate. This is called a baud rate. It's basically how many times per second it sends one bit of data, thereabouts. So there's a bunch of different speeds that things can run at, but the most common one for Arduinos, when you don't need anything terribly fast, is 9,600. So this means they can send 9,600 bytes in 1 second. And that's the speed. In the real world, this speed is limited somewhat by your board. It depends. Different boards can do different fastest speeds, but 9,600 is very well supported, so it's hard to go wrong with that one. The important thing is, in real life, you'll also be able to configure your serial monitor to read at different speeds. You just need to make sure it's reading at the same speed as you're writing, otherwise it'll look like gibberish. But we don't have that problem here. Wonderful, so that's all we need in our setup. Our cereal is all ready to go. Very tasty. You can have your cereal with milk if you like. I'm not one for milk personally, but just preference. And then what we can do inside of our loop is read our analog pin. So to read our analog pin, it's very, very simple. Again, which is good. Arduino is good at making it simple. So you can just do analog read, and then you tell it which pin you would like to read. So actually, right. So I said earlier that variables were optional here because we only need the variable in one place, like the pin number in one place. I won't create a variable name for it, so I'll just put in A0. Now, note that before we could just put in numbers, and that was fine. But here we actually need to include the letter A as well because it's an analog pin. So we're using pin here A0, and you can use A0 through A5. So that's how that works. But what this does is this actually returns a value. So if you recall from like when Python, when something returns a value, it means that this statement, when it runs, gets turned into whatever the answer is. So in this case, if this read some number, it would just put this number into the loop, but do nothing with it. What we want to do is save that number. So we can do, and it gives us an integer, so it's a whole number. So it doesn't give us the voltage directly. There's a bit of a calculation-y thing that needs to happen to convert to a voltage exactly. But what Arduino does is give us a number between, and I think it's this. I think it's between 0 and 120, or sorry, 1023. So what that is overall 1024 different options, which is the power of 2. I think it might maybe be 8 bits. I'll have to double check that. But we can give it some name. So we can say our sensor value is equal to whatever our analog read is. Yes, fantastic. So when we run this analog read thing, it'll give us a value, as Jacob said, between 1023 and 0. So 1024 values total, because we're including 0. And that corresponds to the amount of voltage it's reading across this analog pin here. And that's relative to between 5 and ground. So that'll give us a number. And then with this number, we would like to see it somehow. To see this number, what we can do is print it to the serial monitor. So to do that, we can do serial dot. So again, we're doing something with the serial. That's what's indicated by the dot, or the serial dot. What are we doing with the serial? Well, we're not beginning it, because we've already done that. So instead, this time we're printing. And what we want to do is print a whole line. So when we print a whole line, we do print ln. And that'll print us a line. And then you want to tell it what we would like to see. So in this case, I would like to see the sensor value. Go ahead and put a semicolon at the end of that. We always need those. We could run this code as is, but it's always good to put in a delay in the loop, even if it's for a very small amount of time, because otherwise you'll really, well, in this case, you overwork Tinkercad Simulator and it really slows down. But in the real world as well, you can overwork the Arduino a bit and just, it's just constantly doing the same calculation and never has any time to rest. And no worries if the connection dropped. If you have any questions in a second, once we do this, definitely feel free to ask them. Don't worry if you've missed anything. Stellar. All right, so we're printing it, and then we're just gonna have very, very, very teeny delay of just 1 millisecond each loop, so it doesn't run super fast. This way it's at least a controlled, consistent timing. Stellar. Okay, I think that should be our complete program. So if we go ahead and run this simulation, we'll see, once it starts running, a whole bunch of numbers here, and these look like our maximum number just about. Well, they are our maximum number, actually, 1023. And that is because this dial here, this resistor, is turned all the way over to the positive end. So we can actually rotate this resistor, and we can turn it this way. And you see, as I do so, that number drops down. So about halfway-ish, you end up with half-ish, just about half, actually, of the total voltage, or the value. So we've gone down from our 1023 down to 511. And we can continue that turning all the way down, and once you get all the way to the other side, you get to 0. So this little knob allows us to turn something down from a 0 value all the way up to something bigger. Now, there's a nice thing that they built into Arduino. It's a function called map, and it works in case somehow you're familiar with the Python map function. Very different. What the map function in Arduino does is convert a value from one range into another. So if you know that your value is supposed to be between 0 and 1023, but you want to have a value between 0 and 5, say, it will do that conversion for you. I'm not entirely sure if it will do it with nice decimal point numbers or if it'll automatically convert it to a whole number, but we can give it a go. So I'll double check. So we can double check the formatting of the map command. So if you want to find some Arduino references, you can just check map or whatever the function you're looking for, and then Arduino, and then documentation maybe, or reference we'll go with. Reference. Yeah, there you are. Map the Arduino reference, exactly what we're looking for. So you can see, it does what I said it does. Remaps the number from one range to another. And then here is the important part that we need, is the syntax. So the first value you give it is the actual value that you want to convert, and then here's your range that you're coming from. Here's the range that you want to go to. And it uses the integer master, won't generate fractions. Got it. Cool. So that tells us that it'll give us only whole numbers, so it won't be perfectly exactly what we're after to convert this into a voltage, but it'll give us approximations, and it's kind of cool to use. So we can just put that in here. We can do map, and we're mapping the sensor value, and then our range that we're coming from is from 0 to 1023, and we're going to 0 to 5. And if we run this code, we should get numbers that are between 1 and 5. Okay, so there's our 1 volt, and if we turn it up a little bit, we'll get to 2 volts, then 3 volts, then 4 volts, and eventually all the way up to 5. If we go all the way the other way, of course, we get all the way down to 0. So that is how we can read an analog input with the Arduino. Do people have any questions about this code here? And if your connection dropped and if you missed something, feel free to ask. I'll put up a little poll, seeing if people are understanding it. But yes, feel free to ask as many questions as you may have. I'll wait for a second for people to do that. There we go, there's a poll as well. What's the difference between line 6 and line 7? Let's take a look. So you mean these two lines here, yeah? Yes, so for these two, the difference is, here's where we're actually reading the analog pin. So this stores it into this variable for us. So this is the actual bit that's doing the reading, What this serial print line bit is doing is that's putting it out onto this screen. So if we commented that out, so like, oops, I need to stop the simulation. So if we commented that out, and we ran this, and I cleared this screen, you can see our simulator is running. You can see the time going up, but it's not printing anything out to this screen. Yeah. So this is the bit that does the print, the second bit, and we could also have it do printing without doing the reading. So if we stopped it and we just had, well, we'd have to create the variable somewhere. So we just did analog read 0, and then this, then it would always print 0 regardless of what we do. Oops, just kidding. Of course, there's no semicolon. So if you get an error like this, and if it says something about expecting a semicolon, well, then you've probably missed a semicolon somewhere. Then you can add it in, and then you probably should be fixed. You can see here, serial, just printing 0, no matter what we do, because we're no longer actually reading the value, because we got rid of the reading part. So that's that explanation. And there's another question as well. So, is this value that? Just a worse method to print its value. So, no, that's just a different way to print it. Essentially, that's what map is doing internally, Jacob, is it's doing that calculation that you've given there. This is just, I guess, the more Arduino-y way to do it, because you've been provided it, but you definitely don't need to do it that way. In fact, your way might even let you, if you convert it to a floating point number, get a decimal first. So we can give that a quick go, actually, with what you've suggested. So I think by default, this will give us the exact same answer, but we might be able to do something that fixes that. So sensor value, and then we'll be multiplying by 5 and dividing by 1023. That's not 23, there we are. So this is doing the same thing as that map. If you think about it, dividing by 1023 gives you a fraction of how full power it is, and then you multiply that fraction by 5 because our total range is between 0 and 5. So if we go ahead and run this, and I'll clear that. Well, there's our 0, and yes. So here it's rounding just to those whole numbers again. That's because sensor value is a whole number itself. It's an integer. You can convert between number types by putting the type in front in brackets. So if we did, say, double, which is a double precision floating point number. So a floating point number is a number with decimal places, and this has twice as many decimal places, so it's just a more accurate version. So if we do that and convert this first, this, depending on the order of operations, this might give us the same issue, but we can fix that. Yeah, okay, so there we are. So we're seeing now decimal point numbers, and if we go just tiny bits, you can see it's much more precise, and we get fractions of a full volt. So that's how you can get something a bit more precise. So this does work better than map when you use it like this, but map is sometimes clearer what you're doing. Just depends on how you're writing your code. Does that answer your question there, Jacob? So I don't think it's worse necessarily. It's just a different way to print it. And what's best depends on the context. Cool. Looking at the Discord poll, I've got 2 people that say they understand how the code works. Is that just a low voter turnout, or are there some people with questions still? Oh, it's shot up to 4. 5, wow, look at that. Sorry if I snuck that poll under your radar. Fantastic. Okay, wonderful. If there aren't any questions about this, then we can head on to our next example, which should be a pretty fun one. Ah, yes, we have a button next. So we'll head to a button next, and then we can learn how to use those in Arduino. They're a little bit more complicated than you might think, so we'll jump into that. So just one moment. All right, ready to go. Okay, so we'll wire it manually first, then I'll show you the other trick. So we'll go ahead, we'll do what we did before. I'll download our code before we purge it, just in case I want it. Then we'll go ahead and clean it up. Shop, and clear, wonderful. All right, and then we'll go ahead and wreck our circuit. Goodbye, circuit. It's nice knowing you. Doop, 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 and doop. All right, so the next thing that we're going to try and build is, and we'll we'll start with a serial output of it. Yeah, we can do that. So we're going to use this push button here. So this cute little push button. And they look kind of funky in real life. They're pretty cute. They've got 4 little legs on them. But they're a bit redundant. So let's see if I can find a push button breadboard. Yeah, so that's what they look like in real life. Just like those little cute things. Look a bit spidery. And yeah, and they come in different sizes, clearly. So, how these work is when you press down this button here in the middle, it will connect this side to this side. And at the same time, it also connects this pin to this pin. So you can have it kind of do 2 things at once. But we'll get to see how that works. We only need to use one side of it for the time being. We don't actually need both of them. So this pin here is connected to this pin as well. So this is all one strip of power, and this is another one. And what it does when you press the button is it connects these lanes over to these lanes. So it lets power flow through it. And we'll be able to detect that using an input. And we can use a digital input this time, probably. So I'll go ahead and I'll switch the side that this is on so we're closer to those digital inputs. We'll move this over here. Wonderful. All right. So the first thing that we will do is we're going to need to connect up power to our board, as always. So we'll go ahead and take 5 volts up to 5 volts, and ground. We'll use the close ground up to ground. Wonderful. And then from there, what we want to do is power up our button. So our button will put 5 volts on one side and 0 volts on the other, and then we can read between them. So our first step will be to take, and I'll slide this over a couple, power. We'll make that on this right side here. So this whole right side is a powered half of the button. And then this other half will be the negative half, and that'll be, say, the side that we read or something. Stellar. Okay. Cool. So this whole side, yeah, we'll connect that to our negative. Wonderful. Oops, daisy. Didn't mean to do that. And then we can run power through it, and when we press the button, we'll be able to pick that up. Now, to actually read this value, we'll need to be reading the voltage at some place. So we'll be doing that by reading the voltage here, say, at this H value. So, or H row, column. And we'll connect that up to pin 12, just pretty arbitrarily. Wonderful. All right, so this circuit has a little bit of an issue that we'll run into eventually, unless, of course, anyone knows it right off the bat. But we'll give it a bit of a play first, and then you can see what the issue itself is. So we will... Is that sensible? Yeah, that's sensible enough. So actually what we'll do as an example first, we'll get rid of that one. So, okay. So in code, just add a resistor. Yes. So Jacob is right there. So I would agree. What we need is a resistor. I will show you what happens if you build a circuit like this first, because last year I was in the leg project, and at one point, well, when we were working with this exact pad, actually, we had a kit with this pad in it. We ran into a bit of an issue with these resistors and where you need them and where you don't. So sometimes people think, well, okay, I have power on one side of my button. Then all I need to do is read if there's power on the other side. But there are some complications with that hopefully this might show us. It might not, because it's just a simulation, but we'll see. But Jacob is right, yes, eventually we will need a resistor someplace. Excellent. Yes, and Jacob has also spotted the other one. Look at you, an Arduino expert. Yes, so you can also do a pull-up, what's called a pull-up. Well, okay, so we'll see the issue, then we'll see the solution, which is a pull-up resistor, and we can also see that in software, Arduino lets you turn that on in software instead of needing to add it to your board. So, yes, very on point. Wonderful. So I'll start with a line that just says our pin number. So we'll have our constant integer. This will be our button pin, and that's connected to pin number 12. Stellar. And then we want to set this pin to be an input. So last time, you remember we did pin mode it was. So we had pin mode. Then we had the pin itself, which was the button pin. And before we had output, remember, because we were driving an LED. But this time we want to read a value. So our first attempt, which again we'll run into a bit of an issue here, will just be to use input. So in using input like this, we put in the pin in input mode so we can read from it, which is exactly what we want to do. And then all we need to do in our loop is actually do that reading. So we'll go down to our loop here. And in our loop, what we want to do is read into a variable what our button is doing. So, or actually in this case, what we can do is all in one go. Much like in Python, you have if statements, and these will do something if whatever is up here is true. So I'll want to say if, yeah, we'll do it with a variable before. So, yeah, there we are. Perfect. And we'll go ahead and set the button. So int button state. So this will tell us if it's pressed or not. We'll start with it just not. Oh yeah, we'll just read it here directly. So to read something, very much like how we did digital write earlier, we can do digital read here. So we have digital read, and this will give us either a 1 or a 0 in output, a high or a low value. And then what we can do here is put the pin that we want to read, and that's all we need. Lovely. So now when we go ahead and run this, it'll read the value of the pin at any particular moment through the loop. It'll save it into this variable, and then we can use this variable here in the if statement. We can say, and I'll shorten this in a second to show you a trick, but I'll start with it in the longer form. If the button state is equal to high, so if it's got a positive voltage on it, and it should have a positive voltage when we press the button, because we are connecting this 5-volt rail up here to our input over here on this side. So that's what we'll look at first. So in this case we have, oops, aha, see it indented that automatically. I forgot a semicolon back there. So we'll go ahead and do this, and we have a high, and now if it is high, and just like with functions, you open these with curly braces and you close them with the same. And oh yeah, so we need to decide what we're going to do. I'll let you lot decide. When we press the button, would you like to turn on an LED, or would you like to just print to the serial console? Which one would you like to do? Serial or LED? Any preferences? Serial is quicker. Yeah, sure. I would agree, because we don't have to actually build any more circuitry. Oh, there's a debate. We will start with serial. Depending on how much time we have, we'll jump into LED. I think that's a good idea, because LED is kind of fun to do as well. And combine things. And I can have that as a quiz to reinforce everyone's what they picked up from the last examples. So first of all, we'll try the serial output. So we'll remember what we need for that. We need to set it up. So we'll do serial begin, give it a baud rate. We'll use our default of 9600. Then if our button is pressed, is essentially what this is saying. If it's pressed, because when it's pressed, it should have a high voltage across it. Then we want to print a little message. So we'll say serial, and we'll print line, the button is pressed. And we do something like that. And then we need to remember to close our if statement with this. So that means that it just runs the code between these brackets when it's pressed. And then at the end, since we're sitting here in our loop, of course, it's only polite to add a bit of a delay. So we'll add a delay. Lovely. This should be a good first naive attempt. So if we go ahead and run this, we'll see how it behaves in the simulation actually. So cool. So as you can see, it's curiously reading that the button is being pressed, but clearly the button is not actually pressed. If we press the button and let go of the button, it does not seem to be making much of a difference. So this is the issue that people often run into when they're very first playing with these buttons in Arduino, is that in this particular case, there's nothing really connected to this side of the button. Sure, it's connected to this value, or this pin here, pin 12, that does some reading. But when you put a pin into reading mode, this input mode, what it does is it effectively makes that pin act like a massive, massive, massive resistor. So it's almost as if there was nothing connected that electricity could flow into at all. So very, very, very little ever flows into the Arduino this way. And it has to be that way to measure voltages accurately. But what that means is that even if just a little bit of positive charge builds up on this side of the button, it doesn't go anywhere. It doesn't disappear. It never goes to a low value. It just kind of always stays floating, is what they call it, when something is unconnected to ground or to a positive voltage. It's called a floating pin because its voltage is just left to change randomly. And of course, it's not actually random. It's due to, like, radio waves and stuff in the air. But it's a bunch of this little interference and noise, which is not what you're looking for. So, as Jacob has mentioned, what we can do to solve this problem is add what's called either a pull down or a pull up resistor. And those differ just in the direction that, like, they're kind of connected. I'll show you a pull down first. So that's the external component one. So to fix our circuit, our code is actually, I believe, all right at the moment. I guess we'll find out in a minute. But what we want to do is add a large resistor in here. So this resistor doesn't need to be very small. You don't need much electricity flowing through it. You only need a very, very small current to take this side down to a negative voltage when the button is not pressed. So we can make this a pretty big number. I'll do 10 kilo ohms. I think that's a decently standard size for pull-up resistors. And then what I'll do is I'll connect it between this negative pin up here and this button side here. So now, if you think about it, when this button is not pressed, the circuit is open. So actually, do I have a circuit that I can show you here? Sure do. Let's see if I can open that and then pop it over here. Stellar. So here's an example schematic that we're kind of like similar to. Quite similar to, actually, where you have this switch here, and how these buttons work is essentially if they're not pressed, it's just like a hole in your circuit. So you just have this empty side. So before, we just had an empty side connected to this pin here. We didn't have this resistor. So the problem was that this was just a bit of wire. There was absolutely no power influencing it. So it was just kind of randomly fluctuating between high and low voltages. What we've done now is added a resistor to it that's pulling it down to ground. So when this switch is not pressed, the circuit just looks like this section here. So you don't see any of this stuff. It's just this bit when the circuit is open, when the button is not pressed. So obviously then, you just have your pin 2 connected to ground. So it's going to look like it's connected to ground. You'll get a 0 value, a low voltage. But when the switch is closed, it's also connected to this high 5 volts. And now, because this 5 volt line does not have any resistor on it, it kind of overpowers this low voltage here that's hidden behind this resistor. So the overall voltage at this particular point becomes a high voltage because current flows this way, and the voltage is dropped across the resistor. So over here it's low, but it has to be high on this side of the resistor because the voltage is dropping it. So we'll read a high voltage there. So, to demonstrate that in action, because that's a lot of word soup, if we start this simulation, it should work as behaved. So if we clear the screen, then now you can see it's printing nothing. If I press the button, you can see it prints the button as pressed message, and if I let go and I stop it, then it stops printing. And if I just press it real quick, it only prints it a few times. And that's our nice button press program. So this is one way to do it, and this is a perfectly valid way to do things. However, there's an easier way to go about them as well. So as Jacob mentioned a while back, the Arduino has a way to enable internal pull-up resistors. So a pull-up resistor is just like a pull-down resistor here, except it is basically just connected to the positive rail. So it switches our circuit around a little bit. In our case, what it would do is connect our button to ground. So our button would be connecting to ground, and the resistor is connected to the positive rail. So that's essentially what our pull-up resistors internally work like. So first we'll use this external pull-up, and we'll just show how that we have to change the program. So if you think about it now, when we're pressing this button, we're connecting our reading pin, which is 12, over to this negative voltage. So it should read low when the button is pressed. So what I can do here is set the equals low to be the condition we're actually looking for. And if I run this, and be sure to clear that, then we get the program working the exact same way as before, but with the circuit a little bit different. But the advantage of doing it this way is that the Arduino also has built-in versions of this exact same thing. So what we can do is say, okay, resistor, I don't want you on my board anymore. and get rid of it. And then from there, all we have to do is change our input mode to input underscore pull up. And now, if we go ahead and run that, it should work identically without that external component. So here, you can see there's none of that random noise that we ran into that first time. And if we go ahead and press it, we get a button press, and of course, it works, repeatedly. So that is how you can use the internal pull-ups. One last thing is that these low values are treated as false values. So a low is false and a high is true in terms of like if statements. So if we wanted an equivalent statement to checking if the button state is low, would just be say if the button state, so this would be saying, this would be saying, is the button state high? Because remember, high is true, and if it's true, it runs whatever's in here. So this checks if the button state is high. If you want to check the opposite, in Python, you would write something like not button state, just to flip it the other way around. So this would say if it's not high, which means it's low. In C++, you do that with just the exclamation mark beforehand. So this is an identical way to write what we had before. This is just saying, is the button state low? Because it's asking, is it not high? And this works the same way. It's a matter of style, which you prefer. You might see this one out in the wild, although, to be honest, the other one where you're more explicit about it is certainly less easy to get confused about. So pick your favorite style, I suppose. It's entirely arbitrary. They work identically. Lovely. That is that. Does anyone have any questions about this button pressing circuit? I'll create another little poll, see how people are doing. All right, there we are. We have a poll. Does the button pressing circuit make sense to everyone? And the code as well. You can ask plenty of questions. I know that the pull up, pull down thing is sometimes a little confusing. It certainly has been in the past. So let me know if you have any questions at all about that. I'm happy to answer them. I'll give people another 20 seconds or something to write up questions if they have any, or think up questions. You'll have to see. I assume that people are doing all right. Okay, we've got 4 people that are doing pretty all right. 5. Wonderful. Okay. Well, nobody seems terribly confused according to the poll. If you are feeling a bit confused or behind, no worries. Feel free to ask a question, or you can ask questions afterwards if you're more comfortable with that as well. Lovely. We've got about half an hour, so I reckon we have time to get through one last pretty cool example. Trying to think which one to do next. I think what I'll do is show you some PWM. So that thing I was talking about here with this squiggly line, how that can act like a fake analog output. So I think that is what I will show you next. So I'll get that all prepared. And then we'll go into that. And feel free, of course, to continue writing a question if you have started doing so. Let's take one moment. Find what I was hunting for. Okay, looks excellent. Ready to go. All right, so no questions. Lovely. And 7 people understanding. Lovely. Fantastic. All right. Before, we had a blinking LED that would turn on and off, which was very nice to have. Oh yeah, I probably should have saved that circuit, shouldn't I have? Whoops. But now, what would be nice to do is create an LED that fades smoothly on and then smoothly back off. So a bit like a pulsing as opposed to a blinking light. And this shows off the PWM, or the fake kind of analog output. So first, I'll show you what a PWM signal looks like. So PWM, let's see if I get any pictures of what I'm looking for. Yeah, a little bit. Right. So, okay, and this is even connected to Arduino. Look at that, how convenient. Can you see this decently? Well, it's a bit zoomed out. I'll zoom it in a bit. Even on the Arduino website, how convenient. All right, lovely. So this is how PWM works. It stands for pulse width modulation, which sounds pretty fancy, but it basically just means how long is something turned on versus how long is something turned off. And the idea is that this turning on and off happens really, really, really fast. In fact, according to Arduino, 500 times a second. So when you want to write a voltage of 0 out, easy. You just keep your voltage down at 0 the whole time. If you want to write a voltage that is, well, let's see, this is 25% of the way up there, so this is like 1.25-ish volts. Then you're at 5 volts a quarter of the time, and the other 75% of the time you're at 0. And if you average that, then you end up with the average voltage, which is the analog voltage that you're kind of faking, right? So just to demonstrate, and it's a very simple calculation, how that works, converting between these duty cycles or whatever and the actual analog voltages, you just take the duty cycle, which here is 25%, so that's 0.25, and you multiply by the maximum voltage, which in this case is 5. So this here is faking 1.25 volts. If we do it at 50%, then you just get 2.5, and then plus another 1.5, and then eventually up at 5 volts the whole time. So you think about this can be a way for us to turn on and off our LED smoothly using the Arduino. We can go down from this faking 0 to faking full voltage. Well, actually, I guess these are actually 0 and 5 volts, but faking the in-betweens. Lovely. So that is how that works. Here's where we were. So we'll jump in here and we'll clear our code because we don't actually need this. What I'll do is I'll just rename this button pin to LED pin because we're going to be recreating what I accidentally destroyed earlier. An important bit, obviously when you're doing PWM, is to note that the board, only some of these pins are capable of PWM, so you have to pick one with a little squiggle by it. We'll do 6, same as before, probably. But just be sure if you want to do some fading or anything that's a non-binary voltage, so something that's not just 5 or 0 volts, use a squiggly pin. Lovely, okay. Looks good. We'll go ahead and get rid of all our wires here. Ugh, of course, because the code panel is open, it doesn't let me. Okay, there we are. Shop. And get rid of our button. Sorry, button. Goodbye. All right, we'll bring out our LED. I'll just rebuild the exact same circuit we did a minute ago. So I'll take our resistor that we decided we liked, and that one was connected down to the 5 volts. And well, we'll do it the other way. So we'll connect the negative end to the resistor, and then we'll connect 6, which is our input. This is the one that'll turn it on and off. Yeah, we'll do full power. Why not? So we'll do that. And our negative rail, of course, needs to go up to ground, which is also a ground here. So ground there, as well as 2 over here. They're kind of all over the place on an Arduino. So there we are. Now I can turn off on and off the power with pin 6. And to do so, we just need to complete our circuit by taking this over here to the positive voltage. Wonderful. Okay, so that's our same circuit we had earlier. Whoops, my code is not doing anything at the moment. Yeah, so it's just some empty code. Clear that. There we are. So we have a nice fresh start. And what we want to do first of all, whoopsie daisy, is set up the, whoops, that's all zoomed in, isn't it? Pin mode, so just like we did before. So we'll go into our setup, and we'll set, hello, oh, that's running a simulation, so I can't write the code. So there we go, and we'll set our pin mode. So we've seen this before. The pin mode of our LED pin, which is here, is going to be equal to, or well, it's going to be in output mode. Because again, we're writing out to turn on and off the power for this circuit. So blinking our LED, or what we'll be doing is doing that smoothly so it'll look like fading our LED. Stellar. Now we'll think about how we write a partial value out on this, well, an analog value outwards in the loop. So we'll jump in here, And if you remember what we did, that's very interesting that the indentation is different. Tinkercad is a bit squirrely sometimes. All right, there we are. So from in here, we'll be writing our output. So before, we used a function called digital write, right? So we had digital write, and then we had our pin, and then either a high or low in here. What we're going to use this time is analog write, because analog is something that's not just a 1 or a 0, but it can vary between on a smooth range, which is what we want. In this case, it's going to use this analog write to generate a PWM signal. So we'll jump over here, and we'll do analog, and it's spelled in the American English way, analog write. And then here, you just give it your pin, just like we had before, so LED pin, not lead pin. Although some people do call LEDs LEDs. Drives me crazy. But, you know, to each their own. And then here, instead of using a decimal point number, like saying 50%, it is once again an integer number. But this time it goes between 0 and 255. That's the maximum value, so that's a different range, a different power of 2, because 256 values there. That's a 256 is the power of 2. And you can see it tells us that here as well. You see, highest it goes up to is 255. So, wrong one again. Here we are. So from here, we just want to write a value. Let's start at half power, so 127 thereabouts. And we'll see what that looks like. We'll put in a delay, of course, as to not upset Arduino. It really wants to unindent that some, doesn't it? Fine, I'll let it do what it wants to do. And we'll go ahead and put in our delay. And here we'll do just it doesn't really matter because we're only doing one thing in this loop. So I'll make it a small delay, but slightly bigger than the smallest. Wonderful. Then we'll go ahead and run our simulation. So we can see we have over here a dim, so not fully bright, LED. And that is the result of it being half brightness here. If we were to stop the simulation and make this full brightness, which is 255, you can see the LED looks a bit brighter. It's a bit subtle, admittedly. But, oh, you know why that is? That's because this resistor is way too big. We forgot to change that. Well, I forgot to change that. 165. Wonderful. Okay, there we are. So now it looks a little bit brighter there. And if we were to turn it down to, say, 64, which is a quarter brightness. Oh, of course I need to stop the simulation. 64 down to a quarter brightness, then we turn it on. You get a very, very faint, in comparison, light outwards. Stellar. Okay, so now what we need to do is think about how we're going to smoothly vary this value here down to 0, and then back up to 255, and then down to 0 again. So to do this, we'll set a couple of little variables here up top to make it easier for ourselves. So you can create variables either inside or outside of the loop. So here I'll be creating them outside of ahead of time. Doesn't particularly matter though. So we'll create a couple of numbers. We'll create one called LED power, and we'll set that initially to be equal to 0, so it's initially off. And we'll also have one for fade speed. So we'll have fade speed. And the higher this number is, the higher, or the quicker the LED will change values. So I'll start with, I think I'll start with a fade speed of 5. That seems reasonably quick-ish. And again, the speed here is actually a component of both this delay and this value. So this is pretty arbitrary at the immediate moment. Then what we want to do is, the fade speed is how we're going to change our LED power within here. So to demonstrate what I actually mean, we'll start with and we'll write this to be our LED power. So we're going to set our LED pin to our LED power. And remember, this is a loop, so we're continually going through it. So every time you've set it there, what I want you to do is take the LED power, and I want you to set it equal to the current power, and then add to that the fade speed, just like this. So that gives it, that should make it brighter. Now, just like in Python, this expression here, where you have the variable equals the variable plus something, you can shorten that down, and it's an identical expression just to say plus equals. Just like that. Then we can put on a semicolon at the end and call it a day. So this theoretically, when we run it, should go from a dark LED and then slowly fade up to a bright one, full power. It won't go back down yet. We'll do that in a minute. But if we give it a start, and it might be really quick, so we'll see. So if we go ahead and start the simulation, there you are. So it's faded upwards. Oh, interesting. So it's actually going back down as well. Well, that's quite interesting, isn't it? So perhaps it's, oh, ahaha. And I even know why that is. That's very sneaky too. So this value, when the value that you give into analog write, I think, is higher than 255, what it will do is it will start wrapping around back to the lower value again. So that's what we're seeing here in that little fading, pulsing thing. But that's not exactly what we want our program to actually do. Because we want our program to actually fade smoothly up and smoothly down. Right now it's fading smoothly up and then sharply down and smoothly up again. So it's going a bit like that. To get around this, so just to demonstrate, to show a cool thing, you can do, if you want something to always be between two values, you can use something called constrain. Constrain. And you give the value itself, and you give the range that you want it to be in. So I would like this to always be between 0 and 255. I think I've done that right. So go ahead and run that. Yes, fantastic. Now we see more what I was expecting, where the LED is just staying lit up full power because it started at 0, goes all the way up to 255. We can see that perhaps a bit slower if I change this down to be 1, the fade speed. So slow this fade in down. So we start it, and you can see it fades more slowly up to that maximum power. Now we want to make it so it fades back down as well. So what we need to do is detect when we've hit 255, and then go back down the other direction until we hit 0, and then go back to 255 and back to 0 all smoothly. So one way that we can do this is, because keep in mind every time we're adding our fade speed, what we can do is just make that fade speed a negative number, and then we start subtracting. So we get up to 255, we make fade speed negative, and then we're going down, and we get to 0, then we'll make it positive again, then we'll make it negative and positive, and it'll go back and forth. So to demonstrate what that actually looks like, what we can do here is we can say, once we've reached, we can write an if statement that detects when we've hit a boundary. So if, and we can write a couple things in here. So if our LED power is less than or equal to 0, so if we're at 0 or somehow below, then we want to do this. Or, so in Python you would write out or like that, just in English, but since this is C++, then you gotta make it a bit more complicated for you. Or looks like these two vertical pipe signs is what they're called. Those should be on like your / key maybe. Actually, maybe not. I have a US keyboard layout, so I'm not entirely sure where those might be on your keyboard, but they look like these vertical lines. I'll put them in here so you can see. There you are. And then and is done with the double and sign, and like I said, exclamation point is done, or is a not. So those map over to the Python functions that are or, and not, respectively. Yes, so it looks like they are next to Z. I will trust your judgment. Yes, I think they're probably on the left side of the keyboard then, for a UK layout. But yeah, so those are the ones that you'll be looking for. So that means or, and then what we want to do is if we're less than 0, or the other direction we could be out of boundaries is if we're more than 255. So or if the LED power is more than or equal to 255, then what do we want to do? Well, we want to switch the direction that we're fading. To switch the direction of this fade, we want to change it, remember, from a positive to a negative number, or from a negative to a positive. Now, one operation that can do both of those things, and just flip the direction it's going, is if you multiply by -1. Because if you think about it, if you multiply 255 by -1, or actually, sorry, we're doing the fade speed. So if you multiply 1 by -1, then fade speed becomes -1. So it starts going down. But then once you're going down and you've gone down too far, you do -1 times -1, and it's positive again, and it goes the other way. So you can kind of flip the direction by multiplying by -1. So we take our fade speed, And again, we want our fade speed to be equal to our fade speed times -1. So a trick for that is just your times equals. And we can do our -1 and then put a semicolon on it and go ahead and close that off. Now, theoretically, what this should do is start down at 0, and it should go up slowly to be 255. Then once you've reached 255, it should go back down and turn back off again. And then back on and back off again. So we'll give that a test. And there we are. It's faded up. Is it going to fade back down? Yes, very slowly. It fades down and then it fades back up. It fades down and back up. I think if I change the value of the resistor, I can make that a bit more bright. There we are. That's not quite broken the LED yet, which is lovely. So there you are. So you can see it gets brighter and then darker and then brighter and darker. And we can zoom in, feast our eyes on the LED. Wonderful. So that's how you can write an analog output like that. Now, what if, say, instead of fading this automatically, since we have a little bit of time left here at the end, instead of fading it just automatically up and down, what if we wanted to use our good old friend, the potentiometer, to do this instead? So if I wanted to incorporate this, now we'll do some collaborative circuit building. How would I be able to dim and brighten this LED using this potentiometer? What is the first step? What should I connect this potentiometer up to? What should this be connected to? What should this be connected to? What should that middle bit be connected to? Any ideas? We'll put this one to the audience. Any ideas? What we should connect up the potentiometer to? And you don't have to give me all the pins. You can just give me a few if you want as well. So say, if I put a wire here, where's one of the places I could go with this wire? That would make sense, if you remember from a potentiometer example. If you don't, that's alright as well. Give everyone just another second, a couple seconds. Alrighty, I'll go ahead and show you all then. Seeing as the crowd goes silent. The opposite of the crowd goes wild, I suppose. So, the potentiometer, remember, what it does is, is you connect these two far sides to different voltages, and then you can, by turning this dial, get any value between those voltages off of the wiper, which is this middle line here. So, if I'll connect these arbitrarily, I'll say this left one, you get to be positive, the right one, you get to be negative, and the wiper, we need to be able to read which pin on the Arduino, or which set of pins, should we connect this reading section to? Should we connect it somewhere on this row, somewhere on this row? What are people thinking? Give me a pin, any pin. Analog, I would agree. So I think that's a good idea. And the reason for that is because this voltage here varies continuously. So it's not just a button that's either a 1 or a 0, but it can move smoothly in a range. So we want to connect it up to an analog pin. So in this case, we can be any of those. We'll start with A0. Why not? Stellar. That's actually all we need to do to change our... Oh, aha. Not quite all we need to do to change our circuit. Here, we're currently turning on and off the entire power to the board, which we probably don't want to be doing because that's affecting our potentiometer as well. We just want this to be continuous power now, and we'll just turn on and off the LED. So to do that, we'll change the way this circuit is a little bit. So we'll get rid of that wire. This will no longer go to the whole power of the board, but 6 instead will just power this LED. So 6 is just powering the LED, and then I'll connect this just to constant positive 5-volt power. And that should work all right. And also, I think I can change the color of these. I probably should have been doing that as I go along. Just for the sake of everyone's sanity, it's much easier to look at when I change these colors. That's definitely my bad. And then we'll have our input color be a exciting turquoise, and our output color be what seems like an output color to you. Maybe an aggressive orange, I agree. All right, wonderful. I don't know if that makes it easier or harder to look at. Lovely. So if we want to, let's start by reading the analog output of this potentiometer. What function am I going to need to put into my loop to read a value from the analog pins? Any ideas? And actually, it might be alright if you forget the exact name of it. That's fine too. Alright, that's alright. Suspenseful. So, for reading an analog value, it's all in the name for you there. So, we use the function called analog read, which we saw in a couple examples back. So, here we'll come up with some value. So, we'll call this, say, brightness, because that's eventually what it will be controlling. The brightness will read, analog read, from our A0 pin. So we're going to read in the brightness there, and I will go ahead and chop this away. And so we've read the value of the potentiometer, and that's given us a value, remember, between 0 and 2 or 1023. So between 0 and 1023. So that's what the brightness is. But does anyone see an issue with just directly using this number to control the brightness of the LED? Is there a problem that we have here? Yes, exactly, Luke. So the number range is too big. So this one goes for all the way from 0 to 1024, but the PWM outputs are only between 0 and 255. Now, this one's a bit more of a challenge, but we have technically seen it before. If I want to convert from one range to a different range, what Arduino function might be able to help me? Hey, exactly, yes. So spot on, we can use the map function. So we can do that in several different places. I'm trying to think about which would be the best place to do that. We'll do it in a third line, just so it's nice and clear to people. So if you want to update the value of a variable, what you can do is just type the variable's name again, as we've seen a couple times. Brightness is equal to, and it's all right if you have it on both sides, the brightness value. So we'll be mapping the brightness, and we're taking it from a range that is 0 to 1023, and we're converting to a range that is 0 to 255. And that's how our map function will work. So it just takes the brightness value up here, and it updates the brightness value, makes the new brightness value the mapped brightness value. And that's all right. You can always think, whenever you have something like this where the variable shows up on both sides, it always does what's on this right side with the existing value, and then it does the actual assignment, changing of the value second. So we can go on then and try this. Then what is the last line that we'll need if we want to control the brightness of this LED? What do we need to write out to the pin? Yes, exactly, analog write, stellar. So analog write. And then we'll write out to the LED pin that we have. Oops, not the LED pin, LED pin. And we're going to write out the brightness value. Stellar. Oops, I tried a keyboard shortcut that does not work in this environment. Excellent. And then we can reduce that number or keep that number the same. That's fine. We'll reduce and make it a bit faster. Doesn't really matter because we're no longer printing anything or doing anything with fade speed. So actually we can get rid of fade speed and LED power for that matter. Doop, doop, doop. Excellent. So then we can go ahead and run this code. And we see, dun, 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 it's very bright. And that is because the wiper is very close to the 5-volt side. Now if we take this and we turn it, we can see gradually the LED gets dimmer. Then it goes totally off, and it can get brighter again. So you can kind of measure here and see the difference in the brightness as you turn the knob. Now, there's also probably a way to build this without an Arduino, this particular circuit. But we've seen already how you can use the Arduino to do more complicated things with the numbers you're receiving here. So, for example, you could use this number that you get from the potentiometer, this value that you twist. You could convert from this, big range up here of 1023. You convert that into a range of degrees between 0 and 180, and then you could use it to turn a servo motor. like this one, how you can turn a servo motor by typing things and giving it a place to go. I don't know if that's still actually functional, for that matter. Yeah, okay, it is, yeah. But we'll be learning how to build this next time around. But if you think about it, I'll give a quick teaser, just in this last couple of seconds. The only new part of this really will be using this servo, and for that there's a library, so we'll look at how to use other people's code, import it, just like how we used import in Python. We'll be doing some importing of other people's code to use here for running this servo. But the servo, you just give it an angle, and it goes to that angle. Very easy with this library. And this is basically just a grid of a bunch of buttons. So it's a button here, button here, button here, button here. But you'll also notice coming out of this is only 1, 2, 3, 4, 5, 6, 7, 8 wires. However, the very clever among you, or everyone, will be able to count that there are in fact 16 buttons, because it's 4 by 4. So there are 16 buttons, but only 8 outputs. How in the world does that work? Well, we'll find out next time, with a bit of cleverness. Yes, exactly. 4 rows and 4 columns. I would agree with you, Jacob, and that is the trick that we'll end up using. Yes, you can see, yeah, these say rows 1 through 4, and then down here, columns 1 through 4. Fantastic. Cliffhanger, wow. Tune in next time. Cool, so we're about 3 minutes before our end. Are there any questions that people have about anything at all that we did today, or even things that we haven't done today that you're just curious about in general, like Arduino-ish, or even, I don't know, any of the topics before? Any questions? I'm here to answer. And I guess I'll put bum, bum, bum. Bum, bum, bum. Understanding of this session. There's a poll. Overall, how did everyone do? Was it at an alright pace for everyone to understand? I think this one was better better than the Git one. The Git one I think was very quick for people. If people have Git questions, yeah, there you go. I can answer those as well. I think you have to watch it back and do it because my call dropping for so long. No worries, no worries. I will be on the Discord channel, of course. So if you ever have any questions as you're doing it later on, I will be around to answer them. And wonderful. I'm glad, Philip, that it was good and that you liked it. Stellar. Stellar has been one of my favorite words this evening, apparently. Excellent. Well, if nobody has any questions, then I will free you to run out into the wild world. Next session is going to be, like I said, a bit more of Arduino, and we'll look at that button pad thing, and probably similarly just like work through the practice examples. I'll probably send out a feedback form a little bit later today, and I'll also post up this video as soon as it is done transcoding this evening and uploading to YouTube. So, sounds excellent. I'll stick around in case there are any questions, but if not, it was lovely having you all, and hope you have a nice day. So, see you all. Excellent. Happy to help, Luke. Awesome. Very happy to help. Stella. All right. We're looking a bit feral. Whoops. I'm not going to cut that out of the video. Well, now you know I look feral. Have a lovely day, video watchers.